I want to discuss perspective as pertains to the flat Earth concept. Globe Earthers sometimes challenge flat Earthers, saying, on a flat Earth, the sun would never set. Or they show an image of a distant building with the bottom of the building hidden and say, if the Earth was not curved, why would the bottom of the building be hidden? The common flat Earth answer is it's perspective that answers both of those challenges and questions. Let's take a closer look at one of the common challenges, the idea that the sun wouldn't set. This is the azimuthal equidistant map. It's a very common flat Earth map. And the sun is circling over the Tropic of Capricorn currently. The sun is placed 3,000 miles up. That sun elevation is proposed by many flat earthers due to one or more attempts to triangulate its position. About the furthest you can get from the sun on the flat Earth map is if you are at the tip of South America. And the sun is opposite over the Tropic of Capricorn near the west coast of Australia. But when you draw out that triangle, that results in the sun being more than 8 degrees above the horizon. And here's what 8 degrees above the horizon looks like. That 8 degrees is the best case. The furthest observer, the sun at its furthest possible position, the average observer in North America has an even worse problem. They will see the sun no lower than 14 degrees. And there's 14 degrees, 15. If we move the sun to a different season of the year, northern summer, then that results in the average observer in North America seeing the sun no lower than 19 degrees. Some flat earthers lower the sun. Does that solve the problem? Well, it certainly makes the angles less severe. However, the sun is still unarguably above the horizon in important cases, so in that sense it accomplishes nothing. Meanwhile, it's made other problems much worse, such as simultaneous observations from distant observers. Some flat earthers respond that this geometry accurately represents physical relationships, but does not accurately represent visual perception because it fails to take into account perspective. And that perspective, which is an obviously true thing, explains the visuals just fine. It's important to find out if this is true. Let's do an experiment. This is a clock in my house, and I'm measuring that it is 7 feet above the floor. Now I'm going to measure along the ground at various intervals, 5 feet, 7 feet, and 9 feet. We might draft the problem like this. Here's the floor, and here's the wall. Let's go up to 1, 2, 3, 4, 5, 6, 7, to the top of the clock, and go out to one of our measurements, the 7-foot one, there. And now we can measure the angle with a protractor. It's 45 degrees. Here's the 5-foot position. And we're going to measure that as 55 degrees. Once again, the other was 45 degrees. And at the 9-foot mark, we'll measure that as 39 degrees. So I've drawn triangles to match my room setup. I've measured angles with a protractor, and now I'm going to compare them with observations using my phone's Theodolite app. Let's see if they match. Here we are at the 5-foot mark, and I'm going to raise the crosshairs to the top of the clock. It's hard for me to see my phone's screen right now because it's so close to the ground, but that matches pretty well to what we measured on the triangle. Now out to the 7-foot mark. I'm going to again raise the crosshairs to the top of the clock. 45 degrees, a match. And now out to the 9-foot mark. 39 degrees, great. So what we are seeing is that these triangles accurately predicted what we would see in reality. And there is no correction for perspective in these triangles. If we had tried to correct for perspective, the triangles would have been wrong in their predictions. This experiment leads us to suspect that the sun angle predicted by these triangles would be accurate. Some people may still resist, though, saying that perhaps the effect only occurs over long distances. However, we should be skeptical about that. It contradicts our experience so far, and it's hard to imagine where or when, and more importantly, why, the lowering due to perspective would amplify and get stronger. It's just a wiggly idea that doesn't want to make sense. Still, it's worth thinking about it further. Let's assume that over all that distance, the laws of perspective gradually require the sun angle to be reduced. With that in mind, let's try a thought experiment. Let's suppose that we have a very long, perfectly straight pole. We rest one end of the pole on top of the distant sun and raise the other end to our eye level. What do you see when you sight along that pole? Answer these questions. What direction is the pole heading from your eye? Where is the end of the pole in your view? Where is the sun in your view? So let's list our intuitions. 1. When you sight along a straight object, it looks straight in such a way that the end of it is just right there in the same location as the tail of it. 2. The sun is higher than me physically, so the pole must be heading upward. I must be looking upward from level, above the horizon. If I stand by my intuitions, then the end of the pole will be well above the horizon, and the sun should be visible at the end of it. But according to some people's predictions, the sun is actually lowered below the horizon due to perspective. If the sun is below the horizon, then the end of the pole must also appear below the horizon because it's at the same place. Yet we already know from past experiments that these triangles and diagrams are at least accurate in the short range. So at least the first part of the pole looks like it's headed upward, then eventually bends visually below it. I hope that your mind wants to reject that idea, because in my opinion that would be sane. If it rejects the bending pole, it should also reject the downward bent sun. Furthermore, this thought experiment can be further modified to help us think on the other idea that perspective can be responsible for hiding the bottoms of buildings which are far away. Use the same pole and place that straight pole at the base of the building which is hidden. Then raise the other end to your eye. Now what should you see as you sight along that pole? Again, you are forced to either reject the idea that perspective is hiding the bottoms of those buildings, or else you must come to the conclusion that the pole looks bent. Here's 1-point perspective, here's 2-point perspective, and here's 3-point perspective. Please note that none of these ask us to bend straight poles. All of these lines are straight. But it's important to realize that 1-point perspective, 2-point perspective, 3-point perspective aren't really perspective either. They are artist tricks, which can help them draw perspective sometimes. These have built into them a sort of grid, and they become difficult to use when you want to draw something off kilter from this grid, or when what you want to draw is not easily referenced to the grid. Useful as these techniques can be, don't let them fool you into thinking that in reality there is a single vanishing point or set of points or plane that perspective bows to. In reality, perspective works in every direction in exactly the same way. What I want to work on now is convincing you that perspective is about angles and angular size. We've already shown that drawing and measuring triangles can tell us how high to look for the clock on my wall or anything else. But can triangles and their angles actually help us draw in perspective? I'm going to do a very simple example, and I'm going to do it fast, or else it would take forever. Pause the video at any time if you want more time to think about anything I show. I'm going to draw this object. It's a box, simple and elongated. The face of it is 1 foot by 1 foot, and it's 21 feet deep. Actually, the units could be anything. They don't have to be feet, but I've chosen feet. Perspective needs an observer, so I've placed this observer here, 2 feet to the right of the box, and 1 foot below the box. This observer is looking straight in this direction along this line. And in this direction, the observer is 4 feet behind the box. So now I want to draw point A on my perspective drawing. For point A, we'll draw these triangles. This triangle shows how far to the left point A is from the direction our observer is looking. And this triangle here shows how far above point A is from the direction our observer is looking. I'm now going to draw the triangle which shows how far to the left I should draw point A in my perspective view. Our observer is right there at the center of the protractor, and point A is, I'm going to say, 38 degrees to the left. Now I'm going to draw the triangle which shows how far up point A should be to our observer. And I'm going to measure that as 15 degrees. It's not going to be perfect, but it should be good enough. So now the trick is to draw in degrees. Recall 38 degrees to the left and 15 degrees up. That's where point A should be in our perspective drawing. Now I could do this same thing for the remainder of the points, but that would take a while. Instead, I'm going to use trigonometry. Now stay with me. To build trust, I'm going to have trig resolve the triangles we just did manually, these ones. Trig says that it can tell you this angle of a right triangle by taking the arctangent of the opposite leg here divided by the adjacent leg here. So once again, the arctangent of the opposite leg, which is 3, divided by the adjacent leg, which is 4. It says 36.8 degrees. Now for the other triangle, we need the arctangent of the opposite leg, which is 1, divided by the adjacent leg, which is 4. And it says 14 degrees. Okay, so they don't perfectly match what I measured, but that's purely chalked up to kind of poor drawings and a poor printed protractor. If I had done them perfectly, they would have matched perfectly to the limits of my ability to measure. Here's what it comes down to. Trig lets you put away the graph paper and protractor while still solving things exactly the same as a manual measurement. And it doesn't lie. I know some flat earthers have a deep distrust of math, but if trig did not reliably serve a useful purpose matching reality, then architects at least would toss it in the garbage. I've made this spreadsheet to work with. This first line shows the position of the observer, and the rest of these show the position of the various points on the box. These calculated columns here use math to properly set up the triangles and use trig to solve the angle. As you can see, once again, this matches point A. And copying and pasting the formula down the row, I'm able to solve for the rest of these points very fast. So we plot all the points by their angles into this graph, and we have a perspective drawing. Now let's move the observer. We'll put him a little bit to the left of the box, level with the top of it, and we'll back quite a distance. And here are our new angles. So first let's think intuitively about what our new observer should see. Well, he's level with the top of the box, so the top of the box should be completely flat. Second, he's to the left of it just a little bit, so we should now be seeing the left side of the box. And third, he's further away, so the box should be smaller. Let's go ahead and check that. Here it is, plotted again. The top of the box is perfectly level, and we are seeing the left-hand side of the box. This method, unlike 1 or 2 point perspective, does not flinch at objects which are off kilter. It can handle any object in any orientation if you can feed it the hard data that it needs. Hence, computer graphics are possible. So, these angles are perspective. They don't need perspective added. They are perspective. And real perspective predicts that the sun wouldn't set on the flat Earth model, and that the bottoms of buildings would not disappear behind nothing whatsoever. Some flat earthers get this and try to solve the problems different ways. One proposes that the atmosphere acts like a magnifying glass. Another proposes that it causes powerful and complicated refractions. Others propose the sun is a reflection, a projection, or even a simulation or spiritual manifestation. So committed flat earthers find ways to stay believers. And you might wonder, why do I harp on perspective when they have other ways out? Well, these other ways out all have massive problems of their own, and these other ways are less likely to be swallowed by some honest inquirer who's on the fence. But these would be detected as convoluted attempts to solve their problems in any other way than that the earth is a globe, literally getting in the way of things. Flat Earth have this idea that flat Earth is apparent by using and trusting your senses. And so they are on the high ground. The entire burden of proof, therefore, rests on globe believers. And according to them, every attempt so far has either been a lie or not good enough. But really, they are lying. They don't want you to trust your senses when it comes to many things. They don't want you to think the bottoms of buildings can be hidden by higher water, even though that's what it looks like. They don't want you to think the sun really went down last night. No, it can't do that. It just looks like it. And they'll try to explain it first with perspective and see if you can swallow that. But if you know full well that's baloney, well, here's some other options for you. When they get caught fending off real problems and challenges with corrupted ideas and convoluted theories, then the burden of proof falls squarely back on them. They are the ones with wild ideas sorely lacking proof. They are on the low ground and have much crap to answer for. As one flat earther said, sometimes you just gotta throw stuff at the wall and see what sticks. That is horrible.